Hi everyone, my name is Ivo Buttinoni from Hurricane University in Düsseldorf, and I will be giving this online lecture on phoretic and autophoretic transport in colloidal science, so with a focus on driven and self-driven synthetic colloidal particles. I regret the fact that I'm not able to interact with you in class, but I look forward to a productive online discussion after you have watched this video. And of course, you're welcome to contact me anytime at ivo.buttinoni@hhu.de should you have any questions or curiosity afterwards. So phoretic and autophoretic transport means the motion of micro and nanoparticle due to interaction that occur at a finite interface between the particle and its dispersing fluid. It includes a library of physical phenomena that are alone interesting because it's one of the few ways to drive micro and nanoparticles without the need of applying an external field. However, in this lecture, I will introduce phoresis as a tool to engineer a new generation of colloids known as active particles or artificial microswimmers, which in contrast to classical Brownian particles which only jiggle around in the fluid due to thermal fluctuation, are able to take up energy from the environment and convert it into a net displacement. So these active colloids are intrinsically out of thermodynamic equilibrium and undergo not only diffusion, but also at the same time they undergo subpropulsion. Or in other words, they still wobble around due to thermal fluctuation, but are also equipped with an internal velocity, which I call v in this slide. And the remarkable difference between Brownian and active Brownian motion makes active colloids an ideal playground to study new physical phenomena, such as how active matter clusters, or how it interacts with a boundary, as well as how it can be used to power some micro machines, as well as to form new dynamic phases. Also, active colloids are a very useful model system for living matter, including microscopic bacteria and cells, since their motion can be tuned in order to show analogies with, for example, the run and tumble motion of bacteria, or to the group formation in living population, as well as tactic responses that are the net migration of microorganisms towards up or down a gradient or inside a force field. Artificial microswimmers are also novel building block if one wants to make a new material with dynamic and self-sustaining properties. And finally, these microscopic particles are also envisaged as autonomous vehicles for drug delivery application, as for example it is shown in this video down here, where a U-shaped active particle is used to pick up, then transport, and finally drop off, you'll see in a second, a colloidal cargo. So in this lecture, I will not look into all these applications, but only focus on the basics of subpropulsion. Then I will try to answer the question, how do synthetic colloids subpropel? And to my knowledge, there are essentially two strategies in order to achieve subpropulsion at the microscopic scale. Either use particles that mimic what biological microorganisms do, and therefore resemble the motion of flagella and cilia, which are the legs of bacteria, so to speak. Or the second strategy is to take advantage of phoretic phenomena that are implemented in an autonomous fashion. And this is what I want to talk about today. So the goal of this lecture is to present all different experimental methods in order to fabricate autophoretic active colloids and provide a framework to understand why they move. And here is an outline of of the rest of the lecture. And here I will first introduce the field of interfacial transport, and I will do so by considering the flow of a liquid in small pipes. And here we will ask ourselves what happens when the size of the channel becomes very small, and how do boundary conditions change in this situation. After that, I will discuss the three main mechanisms of interfacial transport, so electrosmosis and electrophoresis, diffuse osmosis and diffuse phoresis, and thermosmosis and thermophoresis, where here the only difference between osmosis and phoresis lies in the different boundary conditions. And finally, I will follow the exact same outline in order to describe how we can take advantage of this phoretic and osmotic phenomena in order to prepare autophoretic colloids or self-propelling colloids. Okay, so let's start. And I want to begin our discussion on colloid transport with a simple experiment that involves that has no colloids at all. And here we consider the flow of an ionic solution, such as tap water, inside a long pipe. If the Reynolds number is small enough, then the flow profile across the pipe is parabolic, and the flow rate Q is given by the Hagen-Poisson relation. So where here this eta is the fluid viscosity, L and R are the length and the radius of the tube respectively, and delta P is the pressure difference. So here this factor, A times eta times the length divided by pi r to the power 4, is the hydrodynamic resistance of the pipe, which, as you can see, increases very quickly as the radius of the channel becomes smaller and smaller. In other words, pumping fluids in small channel becomes quickly very challenging, and large pressure drops are often needed when dealing with a microfluidic device or molecular scale confinement, as well as porous media, and so on. However, when we look at the experimental measurements of flow in nanotubes, we find a pleasant surprise that the measured flow rates are often order of magnitude larger, up to 10 to the power 4, than what is predicted by the simple relationship I've shown in the last slide. And this is shown in this graph over here, where it is plotted the flow enhancement, that is the ratio between the measured flow rate and the flow rate, which was predicted by the formula before. So the question is, what is making life for us easier than expected? Also, a second point that we should notice is that there are massive variation of flow rates in channels of very small size, which obviously depends on the experimental conditions. As an example, this researcher in this article measure the permeability K, which is the inverse of the hydrodynamic resistance, of carbon and boron nitride nanotubes by looking at the flow profile just after the channel mark. And as you can see from this plot here on the right, even though the tubes have approximately the same size, the permeability can be more than one order of magnitude different. Also, the title of this microscope, of this manuscript, includes a clue of the reason behind these seeming inconsistencies. And this reason is leakage. In fact, even though a continuum fluid dynamic description based on the Navier-Stokes equation is valid above 1 nanometer, which is the lower limit for which one can define the fluid viscosity, all the interfacial phenomena which occur near the solid surface, as for example near the channel's wall, are very important in the sub-micrometer range, and lead to non-negligible slip velocities. So in the following, we will not consider what happened below 1 nanometers, and this is a nice review if you're interested in the topic. But we will only focus on surface effect and how this surface effect give rise to slip velocity and transport of fluid or particles. And to understand the reason why surfaces play such an important role in fluid transport at small length scales, we should first realize that in contrast to bulk phases, which are favorable environments with isotopic interaction, interfaces are unfavorable regions where the molecules, atoms, or particles interact differently with the two neighboring phases. On one end, the solid surface, and on the other end, the liquid medium. All this region want to be as thin as possible in order to minimize the interfacial tension. But on the other hand, they never have a zero thickness because these anisotopic interactions have a range. So in this simple and silly example, the thickness is roughly equal to the size of these bits. Now, what happens in these interfacial layers of small, however finite, of small but finite thickness is irrelevant if we look at macroscopic effects, such as the flow of water in an industrial pipe. However, it becomes paramount for example, microscopic and nanoscopic channels or micro and nanoparticle, and is able to lead to the breakdown of the no-slip boundary conditions. And in particular, the coupling between the solvent and the solid surface in the interfacial layers, this coupling prompts us to introduce the definition of a slip velocity, which is the fluid velocity at the outer bound of this interfacial layer, so across this surface sigma 1. And on the other hand, we can also define the slip length, which is the depth at which the extrapolated flow profile goes down to 0, as shown in this illustration here. Obviously, both the slip velocity and the slip length are 0 if we are considering a no-slip boundary conditions. However, unfortunately, it is difficult to identify only one single slip length because many interactions and therefore many length scales come into play at distances from few to tens of nanometers from a solid surface. And this interaction can be electrostatic, entropic, or frictional, or molecular. And this is only to say a few. And we will see some of them in a few minutes when we will talk about phoresis. However, I just want to start by introducing the so-called dynamic slip length, which is only due to solid-liquid friction. So it's only due to the motion of fluid elements near a solid surface. And here our slip velocity is defined by this simple equality over here between our fluid being Newtonian and the stress, which is due to frictional forces, where this zeta is the friction coefficient and this eta is the fluid viscosity. This slip velocity, or equivalently this slip length, is related to the solid liquid molecular energy, and therefore it is related to the wettability or contact angle of the surface. For highly hydrophobic surfaces, in this region here, the slip length can reach a value up to 20 or even 30 nanometers, and therefore affect any fluid transport that occur in the vicinity of the surface. And here's just a recent example where active particles swim near a solid substrate, and they swim by pushing some fluid behind. And here we will see all the details of the swimming mechanism in a few minutes. However, what is important is that here they swim in this direction while pushing fluid in this other direction. And as the contact angle of the underlying substrate changes, as shown in this plot here, this flow profile penetrates, so to speak, more or less into the underlying solid substrate, and as a consequence, the swimming velocity change, as nicely illustrated in this cartoon. And in agreement with what we just said, these changes are significant when we are dealing with a substrate that is highly hydrophobic.